Hello and welcome, and this is the introductory series to basics of volumes inside of Houdini, at the end of which we will create and animate our own clouds. However, before we start doing kind of like this intermediate-ish stuff, we have to understand the basics first. So how do we work with volumes themselves inside of Houdini? So as per usual, let's start with nothing and create some sort of geometry. For example, let's get this squab. I like it more than a big head because it has those prolonged tentacles here, and it will illustrate the points that I have to go through with volumes a little bit better than the big head, which is kind of like a blocky, chunky type of geometry of itself. So how do we create volumes? There are two types of volumes inside of Houdini. One is just the volume, which was previously used for power simulations and for volume visualizations, all that kind of stuff. And a more modern one, which is a VDB, which stands for volume database, if I'm not mistaken. It's a newer, better way of tackling the volumetric data because it does not contain information about voxels that, well, basically do not have information. So let's do the old one first, and we do it with the ISO offset, as you can see. Oops. If I enable this, we have this kind of like foggy looking thing. If I increase the volume sampling diffs, you will see that indeed we have a better resolution. So the other way would be to create VDB from polygons. As you can see, here it is. I do the VDB from polygons. However, you will see that it kind of looks a little bit weird. It doesn't look exactly like the volume. As you can see, it has volumes 1. This one has VDB 1. So it's not exactly the same thing, right? So VDB, by default, it creates SDF, the distance VDB. However, if we disable this distance and enable the density, we will see that we have some sort of looking like this-ish geometry as well. But if we make it 0.2, we'll see that it kind of represents same thing as we had. So what is this voxel size? As you can see, I can increase and decrease the voxel size. However, be kind of careful because the smaller it gets, the more RAM and calculation your CPU will have to do. So can we actually visualize it? Now, there is this thing, it's called particles from volume. Particles from volume, here we go. And we can actually create a perfect grid of particles inside of the volume of the geometry. Then we can do copy to points, and we can do the box. Okay, so geometry to copy will be the box. Geometry to copy to will be, well, those points. I will enable packet instance, and if I enable right now, you will see something with my voice today. You will see that, well, the boxes are a bit too big, right? So how do we fix that? We right-click, copy parameter, delete here, right-click, paste relative references. You will see that now, if I change it, you can see that we have indeed the amounts of boxes that we need. However, I need to 001 to make them ever so slightly smaller. I will disable the packet instance so we can see the topology a little bit better. Actually, you know what? Let's do the poly bevel. Increase the distance ever so slightly. Do the normal. Kind of like this. And if we pack that and instance that, okay. So we have our geometry. As you can see, this point separation is kind of like this voxel size resolution. The last point separation we have, the higher the resolution resulting as in visualized by our boxes right now. However, you can think about these boxes as they were voxels, right? So if I make it smaller, you'll see that we have more resolution. Same goes for our VDB. So if I increase, and by the way, just so we can visualize it a little bit better, we can do the volume visualize, Shift Enter, and for example, we can increase the density by 10 or indeed by 100, doesn't really matter. You will see that this is kind of like blob But if I decrease the volume size, we can see we have more and more resolution and definition of the geometry. And if you see, when I rotate, it kind of has this aliased representation. It kind of looks like the boxes that we had before right here, right? Again, if I make it 0, point, for example, 3, you will see that this right here looks kind of similar, right? So that's exactly what happens. That's the resolution of the voxels right there. So what we can do is we can convert VDB, we can convert VDB back to volume, to VDB. By the way, if we convert it back to volume, you will see we do not have VDBs anymore. We have the old school volumes right there. Maybe sometimes you can think of it as being useful. I don't think it is. Interestingly enough, we can get these volumes and we can do convert VDB and convert it to VDB. So here we had, here we had the volume. Now we have the VDB. So you can see that we can convert back and forth our volumes to VDBs and back again. So it doesn't really matter what we work with. So we can actually convert them to polygons. As you can see, things disappear magically. However, if we tweak the ISO value a little bit, you will see that we indeed have our geometry back. Now, if I decrease the resolution, you will see that our geometry gets, well, practically destroyed. And if I increase the resolution, we have this triangular and quad topology that we can work with. So for example, if I make voxel size 001, you'll see that we have quads that we can work. And of course we can use that. So how is it useful? For example, if we have a box, right? And we have the box and let's say we have like, I don't know, 15 divisions, right? So if we make it as such that we can do the typical mountain, if I displace our geometry using the mountain node, you will see that our edges that were going from here to there, you'll see, right? It's very straight. It doesn't have any additional topology. So when we actually apply mountain to it, they kind of stay in place, right? If we make it positive and increase the amplitude, you will see that we indeed, no matter how much we increase, we have this kind of like topology that stays in place. You cannot, well, basically you cannot do anything about it. And especially if we decrease the amount of resolution in our axis divisions, it will go even worse. So we can do the VDB from polygons, right? Connect it here. Then we can do the convert VDB. We can convert it back to polygons, right? Here we go. If we increase the voxel size, increase the resolution, you will see that we have this kind of result. So in between of those, we can do VDB smooth. You will see that indeed we have some kind of smoothing effect right there. And in fact, if we decrease the voxel size and maybe we increase the iterations of the smoothing, you'll see that we have pretty nice geometry that we can now displace using the mountain. And here we go. It looks much better on those places, right? When we had, let's say we disable this. This edge does not get, treated very well because, well, it has zero topology to be displaced with. However, if we re-enable that, okay, something like this, we can see that this edge gets displaced as well. So that's really useful. Another technique of using that conversion is when we have some sort of geometry that is really, really hard to work with, for example, something that has been destroyed or pre-fractured or whatever. So let's say we have another box, right? And we do some sort of Voronoi fracture, right? And we scatter, we will not scatter anything inside. We will just scatter it here. No relaxed iteration. So yeah, okay, we have everything, and we do the exploded view. You will see that we have geometry that has very, 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 very little topology to work with, right? So what exactly can we do with the VDBs in this example is we can do the VDB from polygons as per usual. It doesn't really matter if we do the surface or density, it will treat it just as well. So then we can do convert VDB back to polygons, and you will see that we have indeed some sort of, you know, kind of maze looking geo, but that was not exactly what I wanted to do. What I wanted to do was to just give it resolution. Now we can do some sort of VDB smooth. You'll see that we indeed have some sort of smootherization going on, if you will, right? Let me just decrease the scale. And if we increase the resolution just a touch more, like 0.05, right? And after that, we can do smooth, in which we will be smoothing the attributes of position. By the way, the smoothing usually gets the filter quality too. However, if we want it to make a little bit more brute force and in this case pleasing to eye, the filter quality will be 1, and it will be just, it kind of treats everything in a manner that it doesn't really respect the curvature of the geometry. So in this case, that is exactly what we want. So basically, you could tweak the strands here and there. You can see that we indeed are smoothing the geometry. And final thing, we can do the normals. Smooth those by face area, make it 180. And that's what we have. This is the easiest way of treating geometry like this, using the VDB conversion, because otherwise you might imagine you would have to do some sort of polybeveling or something like that, then subdivision, then you will have to deal with the wacky normals that will end up eventually. So that is the easiest way to treat geometry. So in further videos, we will talk about creating 3D printed like geometry, and this is the workflow we will be using to make it appear as it was ready for 3D print or 3D printed already, right? So keep that in mind. If you don't want to miss that, just, you know, subscribe to the channel. So what else can we do? Let's create a sphere. Let's make it a polygon with high frequency, right? Let's VDB from polygons. Here we go. Resolution will be, I don't know, 0.03 will be fine. Let's transform it. You will see in a second why we're doing that. And now we can do the VDB combine. Oops, VDB combine. Here we go. Okay, this VDB goes into A, this into B, and this is why we had that transform. So we can basically have two VDBs at the same time. So what do we have is we can do addition, subtraction, multiplication. You will see that this looks kind of weird, and that is because we are working with the SDF, with the surface. If we had density, you will see that. So it kind of treats density in a way that you would expect. So if we convert VDB back to polygons, create ISO value like this, you will see that we indeed have this going on, right? Okay, so by the way, the resampling is if you have VDBs that are of different resolution. In this case, obviously, we have the same resolution because it's literally the same VDB. We just move it around. However, if you had something like this, right? Whoops, something like this, and this was kind of like, let's say 0.07 lower resolution, it will resample B to match A. In our case, the B of resolution 0.07 will be resampled into 0.03, and the result will be this. However, if we make A to match B, you will see that we have much smaller resolution because we treat the 0.07 voxel size as the target for our conversion. So that's pretty obvious, right? So anyway, let's delete that. Let's get back to what we had before, and let's actually talk about the surface. And to make the surface work better, there is actually, as you can see, SDF union, SDF intersection, and of course, SDF difference. So you can see that using the volumes, we can actually do some sort of modeling, right? And of course, if we decrease the volume size, like something like this, right? And then we do the VDB smooth, you can see that we can have some sort of like this smooth result right here. But I just want to make one thing really clear. This is not an ideal way of actually modeling anything like this, because you will see that the normals, right? When you see this reflection here, the normals are really, really bad for any kind of visualization. For precision modeling, this is a no-go. I've seen people using this kind of technique of transforming VDBs and back again and pretending like it's good, but it isn't. It destroys normals. There is another thing you have to keep in mind when you are converting VDBs. Oops, let's copy this to here. Let me just showcase. I will add the end caps, make the, I don't know, 250, whatever. So you can see that we have pretty perfect result. VDB convert to polygons. You can see that, yeah, sure, this is a little bit wonky, but you know, we can work with that, right? Maybe tweak here a little bit and kind of make it somewhat presentable. And from the distance, again, we can make it sort of work, right? However, if we transform right now, if we transform this result, you will see that our edges look pretty good, right? It's nothing bad with it. Well, it does what it says, okay? However, if we do the transformation before we actually convert it to VDB, like that, right? And we actually transform our geometry and start rotating that, you will immediately see the problem I'm trying to, get your attention to. The way VDBs and volumes work is that they actually distribute the voxels in a perfect grid in the X, Y, and Z axis. It does not care for the transformation you had right there. So as you can see, we have perfect geometry right there, right? And if we just rotate it, again, it remains perfect geometry. However, for VDBs, like we said before, they have perfect distribution along the axis. And if this angle isn't being covered by another voxel, we will just create another voxel, just create another voxel, just create another voxel. So particles from volume, just to illustrate my point a little bit better. As you can see, okay, something like this. As you can see, we have this row of voxels here, this row of voxels here, and this row of voxels here. So it will just add perceptually aliased voxel right there. And that is exactly what it does. And when we convert it back, you will see that our topology is very, very wonky. It doesn't look good. It will be a nightmare to work with. So, keep that in mind when you are just, doing the modeling or something like that, that if you have geometry that is aligned well with our axis, it will work just fine. You can see it's practically perfect grid right there of quads. However, if we transform it just a little bit, you will see that we are getting all kinds of problems right there. And it will be really hard and annoying to work with. And of course, it will render and look really bad. However, if you're working with it as in like you're creating asteroids or anything like that, it will be just fine. We can do the VDB smooth again, as per usual. We can do a little bit of smoothing here. We can do a little bit of smoothing there. Smooth, position, right? Whoops. Filter quality 1, right? So it kind of like goes like that. And if we do normal by face area. So from, from this standpoint of view, it will look just fine. And of course, if we have some sort of jagged geometry, as in natural formations of rocks, asteroids, or anything like that, that we will cover in later videos, this will work just fine. But for precision modeling, this is a no-go. So if you see someone promoting this kind of geometry, keep in mind that if you're making it game ready, or if you are working with precise surfaces, this will look like whack. So anyway, that's the basics of working with volumes. Volumes are pretty fun. They're really useful, not just to make clouds or smoke or anything like that, or fire, whatever. It's actually very useful for modeling, but just not for every kind of modeling. But still, we will cover how to utilize the best of what we have. And in the next video, we will actually take a look at volume VOPs, and we will start creating our clouds, and this should be very fun. So hopefully you learned something. If you don't want to miss anything, just hit the subscribe button. If you liked the video, press the like button. You can follow me on Twitter as well. I sometimes write some big brain ideas there. And of course, if you won a lottery lately, you can actually support me on Patreon. This is non-mandatory, but you can get the asset files and stuff like that. Really soon we'll have some premium tutorials going on Patreon as well. And with that said, I hope you have a nice day and see you in the next video. Thanks for watching, and bye-bye.